unconvincing and mathematically non-rigorous way in many of the reviews and books that you may read on the subject. So the research papers are also fragmented because the subject has evolved over time. You know that the rigorous, the subject has been made more and more rigorous gradually. It has not suddenly, it didn't appear in its most rigorous and convincing form right from the start. So let me give you a basic idea of what Bosonization is, and so as the name itself suggests, it is bosonization means turning something which is not a boson into a boson. So that's what bosonization means. So obviously, in nature we know that there are two kinds of particles, fermions and bosons. So naturally, uh, in fact, there is a way of turning one kind of bosons into other kinds of bosons, which I will also explain later on. That was part of that was done by me in one of my early papers in 1998. But that's a separate story. But here, bosonization refers to turning fermions into bosons. But the question is, so, and also it's inverse. See, just like any transformation, like Fourier transformation, it is completely useless unless you can do the reverse also. So you see, Fourier transform, you transform it in one direction, and you should have a prescription by which you can do the inverse also. So, so bosonization is, of course, both turning fermions into bosons, and some people very awkwardly call the inverse as refermionization, but I prefer not to call it that. So it's just bosonization one way and the other way as well. So of course, the next question is, why on earth would you want to do that? Why can't you leave fermions alone? Why do you want to turn them into bosons? There's a very good reason for this, and that is that the interacting Fermi theories typically are written down in terms of pairs of creation annihilation operators. So what will happen is that if you stare at the Hamiltonian of any interacting Fermi theory, it will typically involve number conserving products of fermions like C dagger C with different momentum levels perhaps, but it will involve number conserving products of fermions. So the trick is that there are certain systems in which these number conserving products can be identified with exact bosons. So that is a very special and unusual circumstance. It doesn't happen all the time, but when it happens, it's very useful because you can then map a theory that involves quartic, four fermion. So two body interactions will involve four fermions, two creation and two annihilation. So that can be mapped to a theory of basically bosons which are quadratic, meaning in the sense that it will only have it's quadratic in the bosons and therefore exactly diagonalizable. So the main advantage of bosonization when it works well is that it reduces a theory of interacting fermions to a theory of exactly solvable, eventually non-interacting bosons. So as a result, you will successfully be able to, through the inverse transformation, because you have this inverse mapping also, which connects the bosons to the fermion and the fermions to the bosons, then you can write down the very non-trivial correlation functions of the interacting Fermi theory in terms of the exactly solvable correlation functions of the non-interacting boson theory. So that is in a nutshell what bosonization is and why you would even want to think of doing something like that. Okay, so the rest of the talk will be about explaining under what circumstances this kind of a transformation can be mathematically justified rigorously. Because you can of course do hand waving versions of this in throughout literature, and right from the beginning people have been trying this, starting from David Pines in the in the early days of condensed matter physics, tried something like that in three dimensions. But the mathematically rigorous versions of this, unfortunately, are applicable only in one spatial dimension. So I specifically say one spatial dimension because there is also, relativistic quantum field people, when they say two dimensions, they actually mean one spatial dimension and one time dimension. So it's 1 + 1 dimension. So they say two dimensions very confusingly for some people in condensed matter. They don't know what they're talking about. So I mean, we don't know what they are talking about sometimes when they say two dimensions. They actually mean one spatial dimension and one time dimension. So I've spelled it out. So I really mean one spatial. Time is always one dimension. So space, in this case, there's one spatial dimension and one time dimension. Okay, basically, the language of many-body physics involves the use of creation and annihilation operators of particles. So, since here we are focusing on interacting Fermi theories, specifically it involves the introduction of creation and annihilation operators of fermions. So the question is, why would you use such a such concepts in many body physics? It's because so you can read out all these sentences that I've written down. So we are usually interested in. Uh, can you hear me? I got a bad network quality pop up. Are you able to hear me? Can you
Yes,
see
sir.
and hear?
We can
Yes,
hear.
Can you
sir.
see
Yes,
also?
sir.
Okay, good.
Yes, sir.
So in many body physics, we are usually interested in the behavior of a system containing many particles when they are subject to external disturbances. So so one of the ways of probing the nature of the many body state of a system is to just remove a particle. Just like, I suppose you have a many fermion system, you remove a fermion from your system. Now you see you have a system with one less fermion. But remember that when you had the original number of fermions, that the system was in a many-body state containing many fermions, and it had to, uh, anti-symmetrize its wave function. So that Slater determinant type of thing had to be performed for the original number of fermions. Now you see, once you remove a fermion, then all of a sudden, excuse me, I'll just close the door and come back. Okay, so when you remove a fermion, then the original so now the state is all of a sudden disturbed quite drastically, because now the system has to scramble and find out a way of anti-symmetrizing its wave function for the number of particles, which is now one less than before. So the system is disturbed quite significantly. Now it ceases to be a stationary state because it's going to start to evolve, because it has to again anti-symmetrize in a proper way and so on. So that's the way I look at it. I mean, I just wanted to give you an intuitive feel for what's happening. So that's what's going to happen, that the system will no longer be in a stationary state, and it evolves with time. So now once you replace the fermion, so the idea is that now you wait for some time and then you replace the fermion that you had removed, and then you ask yourself, how is the state now? So after you replace the fermion, the system is now going to have the same number of fermions it had originally. So now it makes sense to it makes sense to compare the new state with the old state, because they have the same number of particles. But then now there's going to be a quantum mechanical overlap between the two, because you have disturbed the system by removing a particle in between. So that overlap is what is called the one particle Green's function, and it is central to the subject of many body physics. So it tells you the nature of the quasi particles in the system. So quasi particles are basically fermions that appear, the fermions that the system appears to be made of when you probe it. Because originally, you see, when you write down the Hamiltonian, The original fermions are the ones which interact with each other and with the external fields and so on. So the quasi-particles are the ones that uh, kind of appear as if the effective fermions that appear almost independent of each other. So the effective free particles that the system can potentially be described in terms of, they are called quasi-particles. Okay, so the one particle Green's function basically tells you information about quasi-particles in the system. Okay, so that's why we are interested in studying the one particle Green's function. So to connect this with bosonization, the one particle Green's function is a very non-perturbative, difficult quantity to calculate, and a technique such as bosonization, when it works, gives you the exact analytical solution for the one particle Green's function, which is very useful. Okay, so now so I'm going to start with some notation, which I think you already know. All of you know this. So C dagger P refers to creating a fermion with momentum P, and Cp refers to this is a point. So this is my Cp is annihilates a fermion with momentum P. C dagger P creates a fermion with momentum P, and because they're fermions, they obey these anti-commutation or fermion commutation rules, which are basically anti-commutation rules. So I think you all know this, isn't it? I'm assuming you all know this. If you don't know it, I mean, I don't want to sound patronizing, but it's possible that there are many students or some students who are new to condensed matter, so they might be confused. So you can stop me whenever you want. Okay. All right. So those are the usual kind of fermions that we all know. But then now the question is, the title of my talk speaks of chiral fermions. So the question is, what are chiral fermions? Chiral fermions are those that come with an additional discrete index similar to spin. Okay, just like spin up down, you have something called right chiral fermion and left chiral fermion. So those are just names. I'll explain to you why they're called right and left, but that's what they're called. They're called right movers and left movers, similar to up spin and down spin. Okay. So now the chiral fermions are special for the following reason. They are assumed to move with a constant speed, and that speed is independent of the momentum. Okay, the speed is a constant. I mean, it's a kind of a just like mass is a constant, speed is a constant in this case. For chiral fermions, speed is a constant. So they move with a constant speed independent of the momentum. So this means the kinetic energy of the chiral fermions is proportional to the momentum. Okay, so then the proportionality constant is the speed. Okay. So as a result, the right movers are considered to have momentum Vf into P, and the left movers are considered to have energy. So if P is the momentum of a right moving chiral fermion, we say that its energy is Vf into P. And if it's a left mover, we say its energy is minus Vf into P. So that's the distinction. Okay. And Vf is an absolute constant independent of the momentum. So it's known as Fermi velocity. So this should remind you of something, and that something is massless relativistic particles, isn't it? Because for massless relativistic particle, E equals Cp, where C is speed of light. But here, that speed, it's not speed of light, it's basically the Fermi velocity. So of course you might think that where in nature would you find such a system, but that's a separate story. We will not address that. I will address that at some stage. Right now, think of it as a starting postulate that we will study systems which are made of chiral fermions. But it's an equally important question to ask, why should we study such a system? Can you show me condensed matter systems made of chiral fermions? That's a separate and important question. but we will come to that little later once we understand the technical details of how to do this bosonization. I'll at some stage tell you that there is a way of coming to terms or making peace with this idea in the context of condensed matter physics. Okay, so the idea is that so if you have right and left movers, you can ask yourself, what is the ground state of such a system? The ground state of such a system is very peculiar. It's peculiar for the following reason. So remember that there is no limit on the size of this momentum. It can be as large or as positively large or as negatively small as you want. So as a result, the right, so the this branch is basically the right mover branch because the slope is positive, and this is the left mover branch. So the perpendicular axis, the vertical axis here is the energy, and the horizontal axis is the momentum. So, and you have a straight line with a slope, and the slope is the Fermi velocity Vf. So here it's minus Vf, and this is plus Vf is the slope. Okay. So now, you see, if you want to populate these, so these are the states. So for a given momentum, you have a certain energy that's possible, but an electron may or may not live there. I mean, you can choose to populate states. States are labeled by momentum, and you can choose to populate states in such a way that you end up with a system which has the smallest energy possible. So now you should ask yourself, how would you accomplish that? How would you go about populating states so that the energy is the smallest? Obviously, the way to do that is to populate the states in such a way that all the negative energy states are filled up and all the positive energy states are empty, because then you will get a system with total energy as negative as possible. So you shouldn't leave out any negative energy state unfilled, because if it's unfilled, you get a lowering of energy by actually populating it with an electron, isn't it? But however, if there is an electron with a positive energy, you should uh, remove it and put it in a state which has negative energy, so that you further lower the energy of the system. So it's very obvious that the way to create the ground state of such a system is to populate all the negative energy states. So which is why I've described this solid lines, um, and these dotted lines indicate empty states. Okay, just aside, are we being recorded? Hello.
Yes, sir.
Yes,
Yes, sir. It is
Okay,
recorded.
yes, sir.
good. Because I would have, I want that because I want to use this later on somewhere else. Okay, thank you. So is that clear? Are we clear about why this is the ground state of the system? Okay. So now Hamiltonian wise, the Hamiltonian operator of such of a system. So remember that we are only talking about kinetic energy. So it's basically the non-interacting Hamiltonian, and so there's no potential energy. So the Hamiltonian of the free theory of chiral fermions would be given by this, where this is the number of fermions, right movers with momentum p, and each of them have energy Vf into p, and this is the number of left moving fermions with the same momentum, and each of them have momentum minus Vf into p. So so that's what that is. Okay, so now because of this additional label, the number of anti-commutation rules kind of multiply, because you have to worry about they're all they're all fermions, right? So the idea is that if unless these indices are the same, it's all zero. The anti-commutations are all zero, except these ones, which is one. So if p dashes are the same and L is same as L here, these are both L. These are both R's. It's one, else everything else is zero. That's fairly obvious. That's what fermion means. They kind of anti-commute with other fermions. Okay, fermions anti-commute with other fermions. So that was all in momentum space. Now we can also I'm going to use this psi later on, but I'm not going to use this too much in this lecture. But it's worthwhile to know that you can also write down the annihilation operator in the real space instead of momentum space. And how do you go from momentum space to real space? It's basically a Fourier transform, isn't it? So you multiply by an exponential function, and these are your components, Fourier components, and you add up over all the momenta, and this is in order for. So you want the psi to be of dimension 1 by square root of length, because you want psi star psi to be have resemble the probability density or something. So that's what this is. But then
Hello, sir.
yeah,
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 I have a question about the anti-periodic boundary condition. How do you define that actually?
yeah. So the anti-periodicity is it's kind of it's convenient, because you see the idea is that we think of fermion as something that changes sign as you go around in a circle. So this was explained to me by Haldane in an email last year. So in fact, all the proofs that I'm presenting is from his notes. So the anti-periodicity is basically to ensure that so if you take a fermion, go around in a circle, you pick up a sign change. If it's a boson, it remains the same sign. Okay, so it's nice to think of it that way, because the mathematics becomes simple. So then what will happen is that the momenta associated with the fermion will always be odd multiples of pi by L, whereas the momentum transfer, see, so when you have scattering between two fermions, so it involves the difference between P1 and P2. You see, P1 is odd multiple of pi by L, P2 is also odd multiple of pi by L, where the difference will be an even multiple of pi by L. So that is convenient. So there is a distinction between so the momentum transfer has a bosonic kind of character, because it's the difference between things, the momenta between two fermionic momentum labels versus. So you will kind of get used to this as we go along. Okay, so don't worry about it too much. So this is an anti-periodic boundary condition that we postulate.
Okay.
So now, so this is so it obeys these anti-commutation rules in real space, and this is a Dirac delta function which is also anti-periodic. So so now let me come to the idea of density of chiral fermions. So normally, if once you have written down the annihilation operator in real space, the idea is that naively you think that its psi dagger psi should give you density. But unfortunately, you see, one of the things about, I kind of glossed over this concept here, which is this idea. So remember that the ground state of the system is populated by fermions. Uh, you see, there are infinitely many fermions here, because there are infinitely many negative energy states. So there's no end to this P, isn't it? So it's like it goes all the way there. But remember that the system is in some sense of length L. So there is an anti-periodicity. So you can imagine that you have fermions living on a circle, right? So you have fermions living on a circle and of perimeter L, and because of that, the system is a finite size, and yet the number of particles living on that system is infinite, because you have to populate all the negative energy states, and there are infinitely many of them. So the number of fermions is infinite, whereas the size of the system is finite. So Formally, the density of particles in this Luttinger model is actually infinity, which makes it which is unphysical, but at the same time, it is an advantage because you can do many things mathematically rigorously because of this, rather unnatural artifact of having infinitely many states but finite size. Okay, so I'll tell you what that is. Well, I'll tell you gradually why it's important to make this assumption, because many things become mathematically exact when you make such an assumption. So, as a result, you cannot do this because the reason why you can't do this is if you take the average, it becomes infinity. So the reason why the average of this is infinity is because, see, why is the average density infinity? It's because the infinitely many particles in a finite size. Yeah. Huh. So on a finite ring, you have infinitely many particles. So that's the reason. So therefore, the only thing of interest would be deviations from that average. So we are not really interested in the average, but we are interested in the deviations, because average is uninterestingly infinite. You already know why it is infinite. So the reason, okay, so the way to do that is to firstly, so as a result, you can't really take the expectation value of this. So what you do is you kind of do what is called point splitting. That is, you replace one of the x's by a different, but very close. So a tends to 0. So it's x plus a and x, and then you take the average of this. This is finite. Okay. So then you look at the difference between that operator and its expectation value. So that gives you the deviation. And when a tends to 0, that gives you the the density fluctuation of chiral fermions. So that would be the correct way. But this is kind of somewhat technical, and also it's fortunately not very important to do this. I just wanted to point out, because when somebody writes down the field operator in real space, and then I mentioned density, the first thing that comes to mind is psi dagger psi. So that should be density, but unfortunately no, that's not what it is in for chiral fermions. So you just have to keep that in mind. But I'll revert back to momentum space, where things are very straightforward. So instead of dealing with real space, which involves all these technical devices like point splitting, um, I would prefer to use momentum space. Okay, so if I'm running out of time or something, you let me know. I still have half an hour, isn't it? Okay, so does anyone have a question or something at this stage? Do you have a question? Okay, so now, so like I told you that instead of defining density in real space, I'll do something which is mathematically cleaner, which is define it in momentum space. So in momentum space, this is what it is, because you can think of this as a homework. Just Fourier transform the q to an x. So you'll get something analogous to psi dagger psi. Okay. But think of this as the mathematically, think of this as the definition of density in momentum space. So I choose to define rho right mover as this, where q is now greater than 0. Okay. So remember that the k's are all odd multiples of pi by L, and the q's are even multiples of pi by L, because the k plus q and k both should be odd multiples of pi by L. So that's going to happen only if the momentum transfer, which is q, is even multiples of pi by L. 0 is excluded. Okay. So now, so for q greater than 0, uh, the right mover density is defined like this, and for left mover density, q is postulated to be less than 0. Okay, so this is how you define density in for chiral fermions. So now, we come to the most important concept in this subject, and that is called chiral anomaly. So normally, you see, you can choose to think of density operator in momentum space in a different way. So if you have, say, quantum particles at location xn, so if you have the nth particle at position xn, the xn is an operator, q is just some, it's just some momentum label, it's just a number. Okay. So x is your operator. So left hand side rho q is an operator. Here xn is your quantum mechanical position operator of the nth particle. So now you can this is how we are accustomed to thinking of density in momentum space. Why is it? Because you see, if you Fourier transform the q, what do you get? Suppose you Fourier transform the q and make it an x. What do you get? On the right side, what do you get? On the left side, you get rho of x. I mean, right? So this is the Fourier component of the density in real space. Think of it that way. So you just make it into rho of x on the left side by Fourier transforming q. So what happens to the right side? Can you tell me? So if you Fourier transform the right side, what do you get? Fourier transform the q, exchange q with x, meaning not replace but exchange in the sense of Fourier transform. What happens to the right side? What happens when you Fourier transform an exponential?
Delta function?
Yes, and it's going to be delta of x minus xn summed over n, isn't it? So the right hand side will be summation n of Dirac delta x minus xn, isn't it? You agree?
Yes, sir. Yes, sir.
Yeah. So the left hand side is your density. So what is that telling you? Basically, density of a system of n particles is zero unless x is exactly at the location of one of the particles where it is infinite. So that makes sense, isn't it? That makes sense, isn't it? Because that if you have, particles sitting at x1, x2, x3, x4, what is the density at position x? It is zero unless x is exactly either x1 or x2 or x3 is somewhere in between zero, isn't it? You agree or not? Do you agree? See, if you have particles sitting at x1, x2, x3, x4, and you want the density at some point x, what is the answer? Zero most of the time, except when x is exactly x1 or x is exactly x2, like that, isn't it? You agree?
Yes, sir. Yes, sir.
Yes.
Yeah. So I mean, I'm trying to convince you that this definition makes sense because its Fourier transform makes perfect intuitive sense. So therefore, this also makes sense because its Fourier transform is obvious why it makes sense, isn't it? Because it's just the sum of Dirac deltas. You agree or not? This is important for you to understand. Otherwise, you won't understand why I'm, you won't understand chiral anomaly unless you understand the straightforward interpretation of density. So this is the straightforward interpretation of density. Is this clear? Okay, so if this is clear, now you see positions of particles by definition they commute with each other, isn't it? They kind of they're supposed to commute with each other. So then if you look at the commutator of rho q and rho q dash, that's going to be zero because that at the same time, I mean, I'm talking about equal time commutations. It's not like, think of this as in the Schrodinger picture where x is independent of time, xn is independent of time. Normally we work in the Heisenberg picture where operators change with time. But now think there's no time. Okay, so it's equal time. So xn commutes with all other xn's. So therefore this should be zero, isn't the positions q is just a number. The operator is xn, but xn commutes with xn dash because the positions of particles are supposed to commute with each other. So we naively expect, or not, it's not naive, it is, if this is the definition, we do expect this. But for chiral fermions, this is not the definition because of the infinitely many negative energy states. We can't afford to define it this way. So that's why there's an anomaly, okay, because this definition doesn't hold for chiral fermions. But if in situations where this definition holds, this also holds. So therefore, there is no anomaly. So the idea is that if the densities for different Qs commute, it's the usual situation. We expect the density for different Qs to commute because the positions at different positions of fermions commute amongst themselves. So, so now the anomaly is that if you define rho properly for chiral fermions the way we did earlier, namely like this, then this does not hold, that the rho commuting with rho for different Qs will not necessarily be zero. And the thing, so anomaly means something unusual. So when density doesn't commute with other members of its own kind, then you say there's an anomaly. So the anomaly means something unusual is going on. So chiral anomaly means it refers to anomaly due to the peculiarities of chiral fermions. Okay, so the idea is that we want to now that this nu can be right or left. Okay, so so we want to really evaluate this commutator. So one nice way of evaluating, so there are many proofs of chiral anomaly in the literature. I have not found any of them convincing, so I invented my own. So the way I prove this is to show that this commutator is actually just a number. First, I prove that it's just, so in other words, I show that this commutator, this Qn, is proportional to the identity operator. That means it's just a number. So the way I prove that this is just a number first is that I show that it commutes with all the fermions, both the creation and annihilation. It commutes with, see, because these are my original objects in the theory. So I either annihilate a right mover or I create a right mover, or either I annihilate a left mover or I create a left mover. So what I show is that it just commutes with every operator imaginable in the theory. So, and every operator imaginable in the theory are constructed out of the C's themselves, isn't it? So if my operator, if this Q commutes with all the C's, then it's bound to be a ordinary number. So this Q is therefore guaranteed to be proportional to the identity operator. So that's what I'm going to prove now. So the proof is straightforward but somewhat lengthy, and it's I mean, for those of you who really want to use this technique and want to learn this subject well, I think you should not skip the proofs. You should kind of work it out on your own and convince yourself. But I have written down the proof in some reasonable detail so that you can follow along if you are really interested. So I have some 20 minutes, so I think I will, since I have taken the trouble of writing down the proofs, so let me actually explain how it goes. So first I try to show that this Qn commutes with the annihilation of the right mover. So obviously, when you take the commutator of C with Qn, you do it this way. So this, I think it's called Jacobi's identity, some version of the Jacobi's identity, if you like. So this is what this is. But then remember that there is the definition of rho. So this nu can be, so if nu is +1, I mean right mover. If nu is -1, it's left mover. Okay, so that's my notation. Sometimes I write nu equals R, nu equals L. Sometimes I write nu equals +1. Sometimes I write nu equals minus. So I mean the same things. So depending upon the so in this context, nu means 1 or -1. So don't put R or L. It doesn't make any sense. So this is the Heaviside step function. So, so therefore, so this follows from the definition of rho. Okay, so now I'm going to insert these here, and then let's see what we get. So so when I insert that, so see that when I insert this here, so then there's a further commutator of a right moving annihilation with a rho, and similarly a rho with a right moving annihilation, because so you have to do it successively. So then there's a further commutation, which again I use the same idea, and then I write down, and you'll find that not surprisingly to me, they cancel out, because I mean, I know that Qn is supposed to be proportional to identity, but when you work this out, they're the same things with a different sign. So like, yes, sure.
So, like when you are talking about the conservation of particles, like here, so it's like you are conserving L and R separately, or the whole system, like R plus L kind of thing. So left mover, right mover.
Yeah, so I have not gone for free fermions. There is no scattering right now. Right movers are doing their own thing. Left movers are doing their own thing. I mean, right now I'm not talking about. I'm not talking about dynamics. I'm talking about kinematics. Right now I have not introduced dynamics. See, this is at the level of kinematics. You see what I'm saying, right? So I mean, it's just commutators. Depends on the definition. I have not committed myself to the system can do whatever it wants. It can either conserve the number of right movers, left movers. That's irrelevant. See right now all I'm saying is if this is the definition of rho r, if this is the definition of rho l, then this is proportional to the identity operator. That's all I'm going. I mean, my goal now is limited. So this is independent of the nature of the Hamiltonian of the system. This statement is a kinematical statement. The statement that Qn is proportional to the identity operator. It has nothing to do with dynamics. You got that?
Yes, sir. Yes, sir.
Isn't it? See, just like see, if you write down the statement that velocity is momentum by mass, that is dx by dt is p by m. That is always true, isn't it? Even if forces are acting, it is force acting, that is also true. So that is called a kinematic statement. But dp by dt depends on force. So how dp by dt depends on x depends on force, but how dx by dt depends on momentum doesn't depend on force. So force can be acting or not acting, dx by dt is still p by m. So that's why such statements are called kinematic statements. Statements which involve writing dp by dt in terms of x. So instead of, if you write dx by dt in terms of p, that's a kinematic statement. But if you write dp by dt in terms of x, that's a dynamic statement, because the answer to that depends upon what forces are acting. So here, this is similar to the first one. So this is a kinematic statement. So independent of what the Hamiltonian is, therefore what forces are acting, it doesn't matter. The claim is that if rho is defined that way for right movers and left movers, this commutator is proportional to the identity operator. So how do I prove that? I show that this Q commutes with all the fermions. Okay. So first I prove that it commutes with the right moving annihilation. Then I show that it commutes with the right moving creation also. Okay, same procedure, except there's a minus sign, there's a C dagger and all that. So same thing. So similarly think of it as homework to show that the same thing it does for left mover also. So it commutes with the annihilation of left mover, commutes with the creation of left mover. So it commutes with all the things. That means it commutes with fermion creation, annihilation, right, left, everything. So that means it is just a number. So it's proportional to the identity. So only identity operator commutes with everything, isn't it? So constant into identity. So therefore, I can write that Qn as a constant into identity. So the proportionality constant, how do you calculate? It is basically its expectation value only. It cannot be anything else, isn't it? Because what can that proportionality be other than its expectation value, isn't it? So now you just go ahead and calculate the expectation value of. So now this rho has been defined in such a way that if you look at the ground state of the system, the rho acting on the ground state is actually 0 because it measures the deviation from the ground state. So the rho's actually measure fluctuations from the ground state. So if you are already in the ground state, rho annihilates the ground states. So because of that, so what is Q? It is just rho into rho minus rho into rho. I mean, it's just the commutator, right? It's rho commutator rho. So it's some rho into some rho minus the second row times the first row, isn't it? I mean, the Greek letter rho. So the first Greek letter rho times, it's basically the commutator. So forgotten what Q is. So this is your Q. So it's just rho Q nu times rho Q dash nu dash minus rho Q dash nu dash times rho Q nu. But then all the rows annihilate the ground state, so its expectation is 0. So as a result, the expectation of Qn is 0, so Qn itself is 0. Okay, so the Qn is 0. But now, so that is not anomalous. So therefore, rho commuting with rho is not anomalous, contrary to the impression I may have created earlier. Because so now notice that you see, unlike because Q is greater than 0, rho dagger is kind of logically independent of rho Q. So rho Q dagger is independent of rho Q because Q is positive. So there are two different objects here. So in the usual way of defining the Fourier component of density rho Q dagger is rho minus Q. So but then I don't allow minus Q there because I want all the Q's to be positive. So I end up defining, so I end up getting two different objects, rho Q and rho dagger Q. So they are logically independent. So because they are logically independent, I am forced to consider this cross commutator now. So this the direct commutator between rho and other types of rho, there is no anomaly. Okay, so they expectedly commute amongst themselves. But then what leads to an anomaly is this one. So if you take rho and take the commutator with its Hermitian conjugate, you get an answer which is not necessarily always 0. Okay, so that's called the chiral anomaly. So same procedure. So first I'm going to prove that this is also proportional to the identity operator. Okay, so the claim is that first I'm going to, so that's the usual trick I play. First I show that this is proportional to this commutator is proportional to the identity operator. So how do you prove that? You show that and this commutator commutes with all the fermions, both creation and annihilation. So I start the same trick and then I do commutator, I get 0. So same with this. So I've left that as a homework. Okay. So to cut a long story short, you can convince yourself that this QA operator, just like the QN operator, I mean the QN commutator, commuted with all the fermions. The QA operator. See, so the small letter A stands for anomaly, N stands for normal or something which is not anomalous. Okay, so Q subscript A stands for that anomalous commutator. So so that commutes with all the creation and annihilation operators. So therefore, it's proportional to the identity here also, right? So the commutator of rho and rho dagger can be written as identity operator times a number, and that number is obviously the average of this, because it cannot be anything else. So now when you go ahead and calculate the average, okay, you get, so remember that rho annihilates the ground state. So what is this commutator? It's rho times rho dagger minus rho dagger rho. So that's what this commutator is, isn't it? But then recall that rho annihilates G, but rho dagger doesn't annihilate G. It's like rho dagger is something like a creation, so it doesn't annihilate. So I end up with this answer. So now I insert the definitions of the rows. So remember that if nu is if nu and uh, so they have to be equal, otherwise you can convince yourself that this from here to here is correct, because if the news are different and or the Q's are different, that is zero. It's fairly obvious to convince yourself. So that's why you have this. But the thing is that you have a distinction. If both the news are R, you get this answer. If both the news are L, you get a different answer. So the Q is positive when there are R's, and Q is negative when there are L's. So you get these two different answers, and this is a straightforward expectation value to evaluate. And then okay, so let's evaluate this. So why is it this way? See, what's happening here? You remember there's a ground state and you're annihilating a right mover. So when can you annihilate a right mover from the ground state? When, what should K be so that you can annihilate a right mover from the ground state? Let me go back to that picture.
Hello? Hello? Am I audible?
It seems, yeah, you are audible, but I think Professor Shethlur has some problem, network problem, it
Yeah.
seems. You can call him on his mobile number maybe, or his office number if he's there. I don't think he's in office.
Nikhil, can you call the sir?
Yeah, I'll call him now. He said,
Can you hear me? My power went off in the middle. Can you hear me?
Yes, sir, you are audible.
Oh, okay.
yeah, we can hear you,
So,
sir.
yeah, sorry. I was trying to ask you, when can you annihilate right mover from the ground state? Stare at this picture. Can you, is that display still visible? Am I still sharing that screen?
No.
No. Okay. Hmm. Wait, this one. So now can you see?
Yeah, it's visible.
So that right mover, left mover diagram, can you see? Okay. So now when can you annihilate a right mover from the ground state? This is the ground state. So I want to operate CKR on this state. So for what values of K can I do that?
It seems for negative values of momentum.
Yeah, exactly. Because for positive values, the ground state doesn't have any fermions here. So this is positive momentum. This is negative momentum, and this is the right mover. So the right movers are all populated for negative values of the momentum. So unless K is negative, I cannot, right? So whereas for left movers is the reverse, isn't it? Okay, so for the right mover, that is what this is. Now, so K has to be less than 0, otherwise it won't work. But then suppose I want to, so K plus Q is not the same as K, remember, because Q is not 0. So now at a different value of, K has to be negative so that I can annihilate a right mover. But then having annihilated a right mover, I want to create a right mover. But remember, I cannot create where I have just annihilated because the Ks have to be same otherwise. So I obviously have to create somewhere else. I cannot create in that hole that I have now just created. But so therefore K plus Q should be what? So in order for me to create a right mover, K plus Q should be. Can I make K plus Q negative? See, if I want to create a right mover, can K plus Q be negative? So this is your negative momentum. I want to create something. Can I create here? Can I create here? Is there any space left for me to create something here? I don't have pointer. Okay, pointer. This one. This is all right mover momentum negative. Can I create here? Can you hear me?
Yes,
Yeah.
Can I create some fermion here? Can I create a right moving fermion here?
No, sir. Like it should be the empty states to create.
Yeah, so but then remember that I have created an empty state here at K, but then K plus Q cannot be K, so I cannot populate that empty space state here. All others are occupied. Can I put another electron here in the occupied state?
no.
No, because
Pauli excellent principle.
yeah, exactly. So right mover, there is no further index available. It's already a right mover, so I cannot put two right movers on top of another. Okay. So therefore K plus Q has to be, if I have to create K plus Q has to be what?
Positive.
Positive. So K has to be negative. K plus Q has to be positive if it's a right mover, isn't it? You agree?
Yes, sir.
So K has to be negative. K plus Q has to be positive. That's what I have written here. K is negative. K plus Q is positive. You agree? Can you see here? That is this first term.
Yes, sir. Yes,
So
sir.
otherwise it's 1. I mean, so the rest of the expectation value is 1. So if k is between 0 and minus q, this expectation value is 1. So similarly here, k has to be positive for left movers, k has to be positive and less than minus q. And otherwise it's 1 expectation. So, and you know how to count. So remember that the k's are all pi by l, 2 pi by l, like that. So if you count, you'll get L by 2 pi into Q. Why don't you do this as homework? So remember that K is what? Minus pi by L minus 2 pi by L up to, but less than minus Q. Okay. So it's going to be like this. So you will get this answer. So when you put them all together, you get the expectation value of this QA operator will not be 0, but it will be this. So this is basically called chiral anomaly. So this row commutes with row, but row does not commute with row dagger. So the commutator of row and row dagger, it is some number. And because it's not 0, it's called an anomaly. It's called a chiral anomaly because this happens only for chiral fermions. Okay. So the anomaly doesn't happen for ordinary fermions. It happens for this chiral fermions which have infinite density but live in a finite region, but there are infinitely many of them. Okay, so so I think now is a good time for me to stop because firstly time is up. Secondly, I have explained the most central idea of bosonization, which is chiral anomaly. But then of course you won't understand fully unless you work out the details on your own. So I'm hoping that those of you who are genuinely interested will work out all the steps and tell me if I have missed something or made an error or something. Okay, so I'm going to stop here if you don't have any questions. So in the next class, I will tell you how to do the rest of it. So how to write down Hamiltonians. So now in terms of this chiral anomaly you can use to define objects which are going to be exact boson creation annihilation operators. Okay, you can already see that boson is going to be proportional to rho basically.
So
So
if you can explain first slide, third line again, so it will be better for me. Actually, the fermions antisymmetric when you remove one fermion from the system, so evolving in
that is
time.
just my way of understanding Green's function. You don't have to necessarily understand it that way. I mean, the way I think of it is that if you have a many fermion system, you remove a fermion from that system, it is obvious that you're doing something very drastic to it, isn't it? You're actually reducing the number of particles by 1. So it takes an enormous effort to anti-symmetrize, n, the wave function of n particles, and all of a sudden one particle has disappeared. Now the system has to again be like a system of fermions, so it will just desperately evolve. I mean, that is my like very poetic way of looking at it. It's probably not very accurate if you take it too literally. That's how I look at it. I mean, basically the bottom line is removing a fermion is a drastic act which will cause the state to become non-stationary. I think that is the technically correct way of saying it. So removing a fermion causes an initially stationary state to be non-stationary. So it evolves with time. And then when you restore the fermion later on, you have ended up with a state that's very different from what you started off with. And then you have an overlap. So you can calculate the quantum mechanical overlap between your starting and state and the final state. That's called the one particle Green's function. And that tells you basically the nature of the quasi-particles, because you see when you remove a fermion from the system, what you end up with is it's like creating a hole. So that hole in some sense propagates through the system, and so by calculating the overlap, you are effectively measuring the properties of that hole. So that's why this is called the hole propagator. Okay, by first removing a fermion and then waiting for some time and putting back the fermion and finding the overlap between your starting and final state. That process and the final answer that you end up with is what is called the hole propagator, because in the intermediate step what you're doing is you're creating a hole, because removing a fermion is the same as creating a hole. So basically what you're doing is you're measuring how that hole runs around your system before it's destroyed eventually, because the fermion is restored to the system. So there is a period in which that hole creates a mess. It disturbs the system quite a bit. So it propagates from here to there and like disturbing the system. And then before it's finally booted out of the system. And then you end up with a state very different from what you started off with. So it's called the hole propagator. And so that hole also behaves somewhat like a fermion, but it's kind of affected. It's not exactly a fermion in the sense that its behavior is not that of the original fermion, but its behavior is affected by the fact that the hole is surrounded by the other remaining original fermions in the system. So that's why it's called a quasi-particle. So by measuring the overlap, you're basically measuring the properties of the quasi-particles in the system. Okay, so that's what the Green's function does.
Okay, thank you.
Is that clear? I mean, it's a very sort of non-mathematical way of explaining, but there is a risk that anytime you explain it in a very verbal, non-mathematical way, there is a tendency for people to take my words too literally and then start asking, but you told me it is this, and then how come it's not that anymore? So don't take words too literally, because finally it's the equations that make perfect sense. The words may or may not make full sense depending upon how literally you take it. Okay. So is that clear?
Yes, sir. Thank you, sir.
Yeah. So I think this is a good time to stop. In the next class, I'll tell you how to define, the ordinary boson creation and annihilation operators in terms of the row and row dagger. And from there, you can exactly write down a Fermi theory in terms of those bosons. So the original theory had chiral fermions, but then now you are able to transform it to a theory involving only bosons, and they're mathematically the same. Okay, so that will be in the next lecture. Okay, I'm going to stop here. Thank you for your time, and thanks to the organizers for asking me to present this, because I've been wanting to do this for a long time, mainly because I felt that I was going to forget this subject very soon if I didn't put it down, in an organized manner. It's all in fragmented places, in emails sent by Haldane and my own notes and so on. So this is a good opportunity for me to organize all that knowledge in a proper way. So thank you again to the organizers. So I'm going to stop now. Okay.
Thank you, sir.
Yeah.
Thank you, sir.
Hello. Okay. So it was a nice talk. So thank you, sir, once again. Our next talk will be given by Shilpi Roy probably on localization, and our talks on bosonization will be given on other days except Monday. We will notify that by through mail actually. So thanks once again for attending this talk actually. Okay, thank you. Bye.